Hi friends, in this video we'll discuss about the motion of a charged particle when it is placed in a external magnetic field. Okay, first of all note this, the magnetic force is given by q times velocity cross magnetic field. Okay, now by right hand rule, if this is my velocity and this is my magnetic field, say the angle is theta. Whatever may be the magnitude, my direction of final force, magnetic force is going to be in this direction, okay, out of the plane. Now you see that the magnetic force is perpendicular to velocity as well as magnetic field. Now why am I bothered about this? Because the work done by any force is given by the dot product of force and displacement. It is nothing but Fs cos theta, right? And you see that the velocity and the magnetic force are always perpendicular. So theta here is 90, so it's going to be 0. I mean to say that force or the work done by magnetic force is always 0. Magnetic field or magnetic force doesn't do any work. Hope everything is clear till now. So how does this particle behave when it is placed in an external magnetic field? If this is my magnetic field, uniform magnetic field, which is going into the paper, and I have a charge plus q, say I'll start from here. Let the charge be plus q and the initial velocity be v. Okay. Now by right hand rule, if this is my velocity and the magnetic field is going into the paper, so by right hand rule, my magnetic force will be in this direction, and this will try to change the direction of my velocity. It, it gets changed like this when it comes here, and like this when it's here, and finally it comes to this point. Here the velocity will be in this direction. Again by right hand rule, magnetic force will be in this direction. Again it tries to change the velocity. By the time it comes here. This is the velocity. Again when it comes here, this is the velocity. So when you join all these points, you're going to get a circle. What I mean to say that when velocity is perpendicular to the magnetic field, this is case 1. Here you see that the particle observes a circular motion. Hope everything is clear till now. And there is something more I need to discuss here. Because the magnetic force is not doing any work here, the kinetic energy of this particle is not going to change. I mean to say that the V or the magnitude of V is going to remain constant. Now, you know that the particle observes a circular path, right? And the magnetic force here always is acting towards the center of the circle. Observe that. So, you know that whenever a body observes a circular motion, it has something called a centripetal force, which is given by mv square by r, where v is the velocity and r is the radius of that circle, m is the mass of body. And here the centripetal force is nothing but magnetic force, right? Which is given by qvb. The magnitude is given by qvb. What can I infer from this? The radius of path or the radius of circle is nothing but mv by qb. Remember this. The same formula can be written as v is equal to qb by m times r. Why am I writing like this? You know that when a body observes circular motion, the velocity is given by omega into r, where omega is the angular velocity. Both these equations are what? Similar, right? So what can we say from this? Omega is nothing but qb by r, where omega is the angular velocity. This is another formula which you can remember. I'm sorry, it's not r, it's m. qb by m is the angular velocity. And note that the angular velocity is independent of the actual velocity v. There's no v term here. It just depends on the charge, magnetic field and mass. This independence of angular velocity on v has some interesting applications which we'll study further. Let's go to another case where v is not exactly perpendicular to v, but you have some component. Okay, see this case. If you have the magnetic field towards the positive x-axis direction, and you have this a charge whose velocity is some random v, and let me divide this into two components, one which is parallel to the magnetic field and another which is perpendicular to the magnetic field. I want to observe the motion of this particle. Now observe this. Because of V parallel, the particle is not going to experience any magnetic force because this is parallel to the magnetic field. Now because of V perpendicular, I am going to experience a magnetic force and I am going to experience a similar motion, similar circular motion as I discussed before. So because of V perpendicular, I want to get a circular motion, and this V parallel, this tries to move the charge in positive x-axis direction, right? So combining both the motions, my particle will move finally in this way. This is a helical motion. Of course, my diagram is not so good, but just try to take it. V parallel tries to push the particle in this direction, so you get the horizontal motion, and this circular motion is due to V perpendicular, or the interaction between V perpendicular and V. Now, the similar formulas work for this also. Just, I mean, the radius is given by Vm by Qb, right? So here it is only due to the perpendicular component, right? So you have to place V perpendicular here, not the whole velocity. This gives you the radius of this helical motion, helical path, and there is something called as pitch. Observe this. Pitch is nothing but the distance between two consecutive circles here. This part, this is known as pitch. How to calculate it? Observe this. The particle has moved from this point to this, and by the time it reached this point, it has covered one circle, right? This time period is nothing but one time period of the circular motion. And how will I get the time period? It's nothing but 2 pi by omega, where omega is the angular velocity. I said you before that qb by m is the angular velocity. So 2 pi by qb, this will be my time period, okay? Using this time period, I want to find the pitch. V parallel is trying to push the particle in this direction. In what time? In one time period, the distance traveled by it will be the pitch. So the pitch will be V parallel into the time period, which is given by this 2 pi m by qb. So this gives you the pitch. Hope everything is clear till now. Observe this scene. Here I have this is x-axis, this is y-axis, this is z-axis. Here I have a electric field in this direction. Also, I have a magnetic field in this positive z direction. I have a particle at my origin, and initial velocity is v towards positive x-axis. Okay. Now, because of this magnetic field, by right hand rule, my magnetic force will be in this direction. Okay. And it also experiences a electric force because of this electric field. It will be in this direction, Fe. So my net Lorentz force will be Q of E plus V cross B. Hope everything is clear till now. Now E is given by, electric field is given by E j cap. I mean, it is in the J direction, right? And B is given by BK cap, V is given by VI cap. Okay, everything is fine. Electric force is QE, you know that. And magnetic force, you know that it is QVB in magnitude, because anyway here the angle between velocity and magnetic field is 90 degrees, right? So it will be minus QVBJ. Magnetic force is acting in the negative J direction, negative Y axis direction. So my net force is this one, QV minus QVB, and this is in J direction towards the Y axis. Here it is negative, so positive minus negative. Okay. What is the condition that gives me this force, this net force, to be 0? When QV is equal to QVB, I mean to say that if the electric field is equal to velocity times the magnetic field, then what happens? This term becomes 0, and hence the net force acted by the particle, it is going to be 0. Actually, this is the condition For velocity selector, I'll explain you in detail. If v is equal to e by b, what happens is uh, the particle moves only in x direction, it doesn't deflect. Now note this, if I have many particles here and each particle has some different velocity, some like this, some like this, some with a bigger velocity. Now I want to separate some particles which have, say, a velocity v, certain velocity v. I want to separate from all these particles. So what I'll do, I'll take the advantage of the above situation. I'll put an electric field here E and a magnetic field in this direction, in the k direction, z axis direction. And if I emit the particles, all the particles in this way towards the positive x axis, what will happen? All the other particles which have different velocities will either get deflected in this way or something else. But only those particles which have the velocity e by b, they go undeflected, and finally I can collect them here. This concept of velocity selector is employed in many devices. One example is mass spectrometer. So I have to set my electric field and magnetic field in this way. Hope everything is clear till now. And there's something called as cyclotron. I'll explain you about that in next video probably. Bye.